This is video 271. I'll be talking about total internal reflection. This is going to be a combination of reflection and refraction. Let's take a look and see what happens. What we have here is a source of light here in an index of refraction number 1 here that is greater than another medium here has a smaller index. So when the light is incident perpendicularly to that boundary, then part of that light is going to be reflected straight back, and part of it is going to go into the other medium. Now we're going to have this light be incoming at an angle. So again, we'll have some of it reflected, the same angle of reflection here, and some of the light will be refracted. What we notice as we keep increasing the angle of incidence, which is right here, as we keep increasing this angle of incidence, let's look at what happens to the refracted ray. You can see we just increased that angle of incidence, and now that refracted ray is bending further and further away from that normal line. So there comes a special angle when that refracted ray is actually 90 degrees. None of the refracted ray goes out into the medium. When all of the light is therefore reflected and none of the light is refracted through to the other medium, none of the light goes through this boundary, we call this total internal reflection. Let's look at another picture here that has all of these cases together. So we have the straight case here, and we can see as we keep increasing that angle of incidence here, the angle of incidence, which is over here, as we keep increasing it, then that angle of refraction, angle 2 here, keeps getting bigger and bigger. Total internal reflection occurs when 100% of the light is reflected. None of it goes off into the other medium. This only happens when the light is moving from a medium with a higher index to one with a lower index. For example, going from water into air. Let's look at some applications of this. One of them is your binoculars. The lenses in the binoculars are far away, much greater than the spacing of your eyes. When the light comes in through the lens here, then as it goes through these prisms, the angles are such so that the light undergoes total internal reflection, as you can see here. And then again, there's another prism, it undergoes total internal reflection here, and then the light is able to go into your eyes. So you can use total internal reflection to bring these rays of light closer together. Of course, you can also use lenses to converge rays of light, but we'll talk about lenses in a different section. Another really cool application of total internal reflection is fiber optics. So with fiber optics, you have light being transmitted, which is data being transmitted through these cables, and the material is such that total internal reflection occurs. So when the data is transmitted over here, you have very little loss into the surroundings, and all of it keeps going through and getting reflected until it gets to the detector. So the total internal reflection is how we get to transmit that data without a lot of it being lost. Let's look at a couple more details of this. We understand the concept, hopefully now, that the total internal reflection occurs when all of the light is reflected. And what we need is an angle of incidence that results in an angle of refraction of 90. So that's this case right here. When light is incident at this angle, which we're going to call the critical angle, then the angle of refraction is 90. So that is not quite total internal reflection, but the criteria here is that if the angle of incidence is greater than this critical angle, such as is this case right here, that's when you have total internal reflection. Here is the equation that we can use to figure out what is the critical angle for any given material. We can use Snell's law to derive this, and I actually like to show this derivation. It's a very quick and it's a good little example here. If we have Snell's law, n1 sine theta 1 is n2 sine theta 2, and we're looking for an angle of incidence. If I redraw this, we're looking for an angle of incidence here. This is theta 1 that results in the angle of refraction, which is right here, results in that being 90. So this is n1 over here. If this angle is 90, well, a sine of 90 degrees is equal to 1. So that means that this crosses out because it's equal to 1. So now if you solve for sine of theta 1, you're going to get n2 over n1. And we define theta 1 as the critical angle. It's the angle of incidence that results in an angle of refraction of 90. And then you know that if your angle is any bigger than this, that you'll have total internal reflection. One last thing we can do here is go ahead and solve for that critical angle by taking the inverse sine of both sides. So the critical angle is given by the inverse sine of n2 over n1. And note that n1 must be greater than n2. You must be going from a high index to a low index. The good thing about this equation, though, is if you happen to mess that up, then you're actually going to get an error in your calculator. So in the next part of this video, I'll go over a few examples